There are basically two types of integrals. The definite integral, which we'll look at now, and then the indefinite integral. The fundamental theorem of calculus. Basically what we looked at yesterday, there you see, f-x, the derivative of the primitive function, I guess is what we're saying. Another way of saying it is we could say, well, d dx of the integral, they cancel each other out, and what we saw was, assuming a is a constant number here, by the way, but x is a variable, we'll end up with function x. Essentially, it's just saying they are inverse operations. How do we play with our integral? Well, that was the first thing we saw. If we want to get back to the primitive function, we add 1 to the power over the power. This one here, see, your integral symbol is a grouping symbol, just like parentheses, just like brackets. You can factorize. However, there is one thing we have to be careful with. We can only factorize constants out. Now, you can't factorize the pronumerals out. So the x's, if it's respect to x, you can't factorize the x outside the integral sign. All this one's really saying is that if you are integrating a series of terms, you just integrate each piece individually. Then this one, if you want to integrate from A to B, you would get the same answer if you just picked another number and said, well, instead of going from A to B, I'll go from A to C and then I'll go from C to B. You will get the same answer. The reason you'll get the same answer? Well, in the first integral, I would substitute in c into the primitive function and get an answer. But in the second one, I would subtract what I get when I substitute c into the integral, so they end up cancelling out. This one here, we know that if the function gives us a positive answer in between a and b, then that integral should also be positive. And the reverse is also true. If I know that function gives us negative numbers between a and b, then that integral should turn out to be a negative number. And if you've got two different integrals but going between the same values, you know that the integral of function x will be less than the integral of g of x if the same is true for the function values. Another way of thinking about that, if you looked at the picture, is if this curve was below this curve, then their integrals would also satisfy the same inequality, because if you're thinking about it, we're talking about the area under the curve. That if this curve was higher, it's going to have a bigger area. This one can be useful. If I want to swap the limits around, I can do that. However, it will change the sign of the answer. So if you swap the limits, you then change the sign in front of the integral symbol. Making use of symmetry. If it is an odd function, then I know going from minus a to a, so symmetric around 0, that integral will be 0. Now that comes back to what we said about the integral being negative if its function's negative, and it'll be positive if the function's positive. Let's just look over here, our cubic for instance. So if I was going from negative 2 to 2, well, from negative 2 to 0, the curve is completely below the axis, so completely negative. Therefore, that integral would be negative. But on the right-hand side, I'm going between 0 and 2, and there the curve's completely positive, so the integral will be positive. But by symmetry, we know the actual area would be the same size. So if one's positive and one's negative, and they're the same size, then you'd add them together, you get 0. With even functions, for this one, again, I can make use of symmetry. I can say, well, look, I'm just going twice from 0 to a. If I look at the parabola, in this case, I could say, well, if I'm going from negative 2 to positive 2, from negative 2 to 0, there's my area. On the right-hand side, it would be exactly the same area by symmetry. Therefore, you get twice. That can be useful because often 0 is an easy number to substitute in. And when you're looking at your functions, remember things like this. If I've got an odd function times an odd function, I get an even. Odd times an even, I get an odd. And then even times even, I get an even. So basically, if they're the same type of function, when you multiply them together, you get an even function. If they're different types of functions, you multiply them together, you get an odd function. Let's do some examples then. Integral of 6x squared dx. I could factorize the 6 out and then just integrate the x squared. and I'll get a third x cubed, add 1 to the power over the power, substitute in, we get our answer. The cube root of x, so I've got to change it to index form first. So that's x to the power of a third, add 1 to the power over the power. 4 thirds over the power, when we're talking about fractions, is the same as saying what's the reciprocal. So I'll get 3/4 x to the 4 thirds. Substituting 5 into this, I'm not going to get a nice, neat, exact answer. If I go to a calculator, I'll get a decimal approximation. If I want the exact one, that's where going back to surd form becomes useful. So it'll be x times the cube root of x. I end up with 15 times the cube root of 5 over 4. Sine, hang on a sec, how do we integrate sine functions? We haven't really looked at that yet, but this is more making use of the odd and evenness. See, we have the symmetry around the origin from -2 to 2. Now sine is an odd function. We're doing that and we're going sine times sine times sine times sine times sine. Well, okay, sine times sine, that becomes an even function, but then times sine, it's now back to an odd function. Now times sine again, it's now an even function. Sine to the power of 5 therefore must be an odd function. So actually I don't have any work to do here. Oh, well that's just 0, because an odd function to the power of 5 will end up being an odd function. Here I can also make use of symmetry, because I've got a mixture there of odd and even functions, but I know all the odd functions will end up being 0. I could rewrite that in a much shorter way. I can say, well, that's twice the integral from 0 to 1, and I'll just pull out the even functions. 2x squared plus 1. Integrate that, substitute in, I get my answer. There's this thing called sketching the signed area function, which is a really fancy name of saying, hey, let's draw the primitive function. This is the area function. This is what we've been looking at. We're saying that the area would be the integral going from a to x. Now when we did it we said from 0 to x, but a could be any number. Most times we do 0, but it doesn't have to be. And we know that will be substitute into the primitive function for x minus substitute in the primitive function for a. Now using that idea, if this is my function, I'm now going to draw its primitive function. I'm going to call this area from 0 to a just capital A. Now I'm assuming here, to make this question a lot easier, that these are all nicely this a as well. So the area from 0 to a, I'm saying, is going to be the same as the area. It won't be the same as the integral, of course, because some is above and some is below, but it'll be the same as the area from a to b, which will be the same as the area from b to c and c to d. So in other words, I'm saying they're all equal to a. When I draw my derivative graphs, primitive function graphs, I like to put them above each other vertically, and so I can just translate up and down. My key points then on this area function that I'm drawing, the primitive function, are a, b, c and d. So I've plotted those points at the x-axis there. But what can I do? Well, I know area A is equal to 0, because look at my little formula here. I would be saying the integral from A to A, so it'll be function A minus function A, which is of course 0. Okay, I know I've got an x-intercept at A. The other interesting thing about this x-intercept, it must be a stationary point. Remember, function x here is the derivative of the area function, and we're saying at A the derivative is 0. So I also know that's a stationary point. Well, let's find the y-intercept here. So what would area 0 be? Again, going back to my formula here, I'm saying it's the integral from a to 0. Well, that's where I'm going to use that idea of swapping the limits around, because it's easier to look at it and say, what is it from 0 to a? But I'll change the sign. Now we know from 0 to a, we said that we called that capital A. So my answer is going to be negative a, because it's the negative of that area. So bang, there's my y-intercept at negative a. Okay, what about area B? Well, area B, I can see it here, it also has a value of a, so therefore, but it's below, it's got to be negative a. I could also go back to the formula and do it that way and say, well, hang on, it's going to be the primitive function of b minus the primitive function of a, and I could work it out that way as well. B would actually be a possible inflection point. Because again, have a look at it. Its second derivative must be equal to 0, because if I look at its derivative graph at B, I have a stationary point. Therefore, the derivative of the first derivative is 0, i.e. the second derivative is equal to 0. We have a possible point of inflection there at B. Area C would be negative 2a. I'm simply adding another a. It's below the axis, negative 2a. Plot that one in. It's also a stationary point, because if I look at my derivative graph, it's equal to 0 at that point. And then finally, let's work out area D. Area D, I'm now adding on another a. It'll go from negative 2, add on a, it's negative a. But then it will just keep increasing. So if I look at my derivative graph, as I go past C, that curve is staying positive. Therefore, this graph must be continually increasing. Let's draw it in. There's our graph. Bingo. 5C and 5D.